ser mejor, puedes ver lo mejor que fue la serie de la película de Página. ¿Cuál es el título? No lo sé. Bueno, pues un placer presentar a Mike Shub con Perspectivas Matemáticas. Él es una persona que trabajó mucho tiempo en cosas de sistemas dinámicos y ahora es bastante, se mueve en muchas direcciones y nos va a hablar de tópicos en donde están intermezcladas varias áreas. Entonces es una plática rica en este sentido. Y según me comentaba Santiago, nos promete muy buenos resultados y muy buenas ideas que presentamos para la plática. No es la primera vez, ¿verdad?, que está aquí. Pero en este instituto, en este edificio, supongo que es la primera vez. Ojalá siga viniendo muchas veces. ¿Qué se puede? Bueno, gracias.
Thank you. Actually, I was gave a talk in Cuernavaca Friday, and there Oveen took a picture of me, my arms up like this, and sent it to me. I showed it to my wife, and she said, "Oh, I know that picture. I've seen that picture before." And then I remembered, oh yes, on my website at the University of Toronto, where I haven't been for 7 years, and I haven't touched my website in 7 years, but apparently it still exists functionally. There's a picture of me with my arms up like that. It's my picture that I've chosen to put on their website. And the picture was taken in this institution in 2008 when I gave a talk here. I think today I will likely repeat myself a lot, but I presume the talk is not fresh in your mind anyway, and perhaps a little repetition won't be so bad. Also, let me apologize that I'm not speaking in Spanish. It would be much better if I was, but I'm just not capable, at least not yet. So, what is the subject matter? I have a lot to say, and I tried to prepare a talk that is very concise, and, but it has a lot of content. I think the subject is a very exciting subject, and it's been recently made a lot of progress. So let me try to fill in what the subject is about just by starting by saying something about numerical algorithms. And criteria for numerical algorithms. So one, so if you look at a numerical linear algebra textbook, they may tell you about iterative algorithms to solve a problem. And what they'll tell you is the criteria that they will use is the cost of one application. So let me say, I'm talking mostly about iterative algorithms. So you're supposed to do something, and then you loop, and you do it again, you loop, you do it again, you loop, you do it again, until your answer is satisfactory. So that's the iteration. So then they say the cost of one iteration. Then they ask for the performance in the tail. That is to say, as you approach the answer, how is the accuracy increasing? So you may, for example, find that it doubles precision in each application in the tail. Maybe triples Or maybe it's just geometric, so-called linear. So these are criteria for what happens at the end. So like Newton's method. We all know Newton's method doubles the precision, it's like the square every time. So Newton's method doubles the precision, the number of digits of accuracy of your answer doubles every time when you're near the solution. So that's a type of criteria. Third one is accuracy and stability. How accurate is your algorithm? How stable is your computation? And then they will, what they may do is they will try it out on a set of test problems. So there may be, to compare different algorithms, there's some collection of problems out there that someone has specified, and then you try your algorithm out on this collection of problems and see how well it works. So finally, if you're happy with all that, then there's experience. Really, how does it work in practice? So this is a methodology. If you look at numerical linear algebra books, I think you'll see this, this type of criteria entering in. And in fact, when I was working at IBM, that's what we did a lot. They had to design new algorithms. Every time there was a new machine and a new language, they had to redesign their numerical algorithms. But there's an alternative, and the alternative that, so this is this other approach. And it's borrowed from computer science. This approach is complexity theory, and I have to tell you what complexity theory is. Complexity theory. So the first aspect of complexity theory is that you have a well-defined set of problems. Well-defined set of input problems. So an instance is an input. So what are examples? So an instance is an input. So what are examples? A. I may be inputting n by n matrix A. So A is an element of m, and some field. I'm going to take the complex numbers. So m is an n by n matrix with complex entries. We might do any field, or the reals, in particular, rationals. But what I'll be talking about today is mostly the complex matrices. Or we may input a degree D polynomial. This is going to say, let's say AI is a complex polynomial. So then the space of these will be the P space, I'll call it PD, equals the set of such F. Another example of specific, maybe I'll put the C here. Another example would be n polynomials in n variables. So then I have f I, so I equals 1 to n, fi of x1 through x n polynomials m, I equals 1 to m, n variables. So I have n of these expressions, and they're of the form a, I, x to the I. So I is a multi-index. And these are integers whose sum, positive integers whose sum is some particular d. So I'm going to say n polynomials and n variables of degrees di. I equals 1 n, and then I'll take space of these. So one polynomial will be, I'll call it an HDI, or PDI, and this will be the product of PDI, I equals 1 to m. So this f is in here. F. Oops, this is getting a little too messy, isn't it? So these are polynomials, I equals 1 m. These are multi-variable polynomials, complex polynomials, each one of degree n variables. The degree, the ith one is di. This is the whole space of them. The ith one is the space of polynomials of degree I. Now we take the product of n of them. So that's definitely a well-defined space of inputs. And let's see. I have a couple of more examples. B is n homogeneous polynomials. In n plus 1 variables. Note here I have very different n and n in the general situation, but here I've just taken n homogeneous polynomials and n plus 1 variables. So then I have f1 of fn, and I'm going to specify their degrees again. So of degrees, write the degrees as a vector. So I have f1 through fn, and fi is an element of homogeneous polynomials of degree di. And so f is an element of the product of these. So that's a big vector space. These are big vector spaces over the complex numbers if I have complex coefficients. This is the context of Bezout's theorem. Bezout's theorem is supposed to tell you that there are product di zeros generic. Okay. So now the next thing is you're supposed to have now we have a very definite space of inputs for a problem, and now we also have to have a very well-defined notion of what a solution to the problem. Well, let me give you examples of problems and solutions for A. A, we could ask, is determinant of A equal to? Then you answer yes or no. That's your problem. You're supposed to determine is the determinant of A equal to 0, and you would output yes or no. B. So that was the question of n by n matrices. B is univariate polynomials. You may ask, does that have a degenerate 0? Oops, move those 0. And you output yes or no. C, you may ask, for example, does there exist a 0 of the system? That is to say, a point x0, x1, up to xn, such that fi of x1 up to xn equals 0 for all I. I give you m equations, I ask you, do they have a common 0? And you output yes or no. For D, well, D is supposed to have zeros, there's no problem. C doesn't arise so much for question D, there are always zeros, and in fact there should be a lot of them. So you might ask for D, find a 0. I'm going to give you another problem for A. Find eigenvalues and eigenvectors of A. That is to say, lambda V such that A of V equals lambda V and V is not 0. So these are examples of problems and kind of well-defined solutions to the problems. What else do we need for a complexity theory? Is the notion of size. So we need a notion of size of the input. So in case A, for example, I've got n by n matrices. I'm just going to take, in these instances, the dimension of the space of inputs, which is just, in the case of matrices, the number of non-zero entries, it should be n squared. In the case B, of B. Polynomial systems, it should just be d plus 1 for the number of coefficients you need to write the univariate polynomial. In C, it should be summation of n plus di, choose di, I equals 1 to n. That's the number of possible coefficients that you have of such a system of equations where this is the combinatorial number. And for D, it's the same. And the next thing we need is a notion of cost. Cost of the computation, of using the algorithm And here I'm going to take the number, the total number. So this is total number of arithmetic operations. And comparisons. So you may ask, is something you computed 0 or not? Is it bigger than 0? This is the cost. Now what's complexity theory? Complexity theory is to consider cost as a function of size. So complexity theory is to consider cost as a function of size. Now notice this is the total number, so this is different than what the numerical analysis situation is, because this is the total number of operations, and here you've got how many operations you have to do for one step, but you don't know how many steps you have to do. So this cost allows the cost of adding up the cost of all of the steps. This one gives you a cost of just one step and tells you some information about the tail. So what is the situation in linear algebra and the eigenvalue problem? The situation is that there are algorithms for the eigenvalue problem, which in practice work very fast, satisfy all of those conditions, and everybody in the numerical linear algebra world is happy with the situation. But they haven't done this type of analysis, which would tell you what is the total cost as a function of the input. So there's some disconnect. And in fact, I think understanding this really, really well for the numerical linear algebra situation is still an excellent problem. To understand how practice relates to theory, and can complexity theory even help you to maybe improve practice. So there's a class P is problems with cost polynomial in the input side. So there is some polynomial such that the cost is less than the polynomial of the input side. And here, of course, is the great problem. You get $1 million if you solve it. In this context, there's the problem that's being I don't want to spend too much time on this, but this is the context, and there's a whole theory, class of polynomial time problems, the ones that you can solve in polynomial time if someone gives you a hint, and tells you the answer, then you can check it. And the question is, are these classes of decision problems the same? So that is a wonderful thing, and I can refer you literature. There's a book that Lenore Blum and Felipe Kruker and Steve Snell and I wrote called Complexity and Real Computation, where this context is done in the context of regular computer science theory, but also in the context of these types of problems that I'm discussing, which aren't 0-1 problems. These are complex number problems. So that's a different universe. So what's the story here? What's the story? This one's in P. You just take your Gaussian elimination argument to figure out what the determinant of the matrix is. And you do it in n squared or n cubed steps. So since the dimension is n squared, the cost is like n cubed, it's polynomial. So that's, this one's a key. This one is also a key. Because you take the discriminant of the polynomials, f and f prime, you see if they have a common root. The discriminant has a definite formula to it, so you just calculate it. You answer this question the polynomial time. C, this problem is NP complete. So, if you can say anything about it, great. D, find a zero. But we know, even for complex polynomials, we can't find a zero exactly just using arithmetic operations and comparison. So the problem doesn't actually make sense. And same here, you can't find the eigenvalues and eigenvectors because if you could solve the polynomial. So we have to do something better here. We have to extend our notion. So here, up till now, I've been discussing problems that have a definite answer that you can't compute, they are decidable. Here, I'm talking about search problems, not decision problems, and you can't find things exactly. So you would have to enter into a world in which approximation to an answer gets somehow inputted into the notion of the size or the input of the criteria that you want for a solution. So now we have to talk about approximation, we have to enter with the notion of approximation, and ultimately even, we will have to discuss what happens if you have imprecise input information. Like you're collecting data from sensors, and the sensors are not exactly accurate. So you have imprecise input, and then you're using the computer machine, which only does arithmetic up to finite precision. Now a whole other collection of issues might arise here. Some of them already, where the numerical people know it, they had to talk about accuracy and stability, and they do a very good job of doing that. But we have to incorporate that somehow into a theory. And ultimately, we'd like a theory that admits sort of reductions, so you could have things like NP, and you could compare how some problems are more difficult than others, or if you could reduce this type of problem to that problem, and how costly is that reduction, and how stable is it, and etc. Of course, in numerical analysis, the tendency is we're going to reduce everything to linear algebra. So it's either solving linear equation or it's solving the eigenvector problem. So to understand how good that reduction is, that should be a portion of complexity. Okay, so there has to be, there has to be a notion here of the sensitivity of the solution. So this is a notion that actually I think, as far as the computational world is concerned, began with Alan Turing, actually. He wasn't talking about zero-one machines of logic anymore, but he was talking about real computer machines that are computing scientific problems, like solving linear equations. So there's this notion of conditional. more or less, the condition of a problem should be more or less the condition of a problem instance. Should be more or less the derivative dissolution problem. Maybe the sign. No. I'll put a norm there. How sensitive is the solution of your problem to your input problem? More or less. Sensitivity. Maybe made relevant. Sensitive is the relative error in the solution to the relative error in the input problem. Okay. So for linear algebra, just for linear algebra, you want to take AX equals B, and you want to study what happens if I take AX plus del X equals B plus del B. And I want to understand what the relative error in X is compared to the relative error in B. So I want to consider del X over X. These should be norms compared to del B over B. And del X should be estimated by the norm of A inverse times del B. Take A inverse, you solve for del X in terms of del B, and that's divided by A of X equals, let's see, over X. And the norm of del B over B, but that's at most the norm of A times the norm of X. Let's see, this is equal to the norm of A inverse times the norm of A. So this is the condition number of the linear map A. Condition number of A and norm of A times norm of A inverse. So there's a whole book written on condition number now by Borgese and Cooper, which I recommend. So that is somehow going to have to enter into our analysis, ultimately, if we're going to be talking about computations that aren't exact, inputs that aren't exact, and we want answers that are pretty accurate, we're going to have to take into account somehow the condition of the problem instance. Now let me say something. That's sort of when things aren't exact, right? But it does seem to me that the N versus NP problem may be different. The P versus NP problem may be different in this context. Because when the situation is very sensitive, it is difficult to check the answer. So a very sensitive instance may be no harder to solve than to check, because the sensitivity already will enter in, as we'll see in a few minutes, into the arithmetic cost of solving the problem. So it may be that the P versus NP problems, of saying something very controversial, might be different in the numerical analysis world than it is in the logic. And that is really something that could be very exciting as a development of the theory. So what is the, let me just say what the condition number is for the two problems of interest. This was the homogeneous, that we were supposed to find the answer. So in problem D, a C, which was homogeneous, which was that? That was D, homogeneous systems. So for D, the sensitivity of a root of a homogeneous system is somehow related to the linear sensitivity, and it is, we define it as the condition number, mu, so this is the condition number. Mu of fz, where f of z is 0, this is the norm of f times the norm of the derivative of f at z. Now, let's remember that in the context of homogeneous systems, the zeros are lines. They intersect the plane z0 equals 1 in points, and but the zeros are lines. So if I take a 0, the function is going from n plus 1 space to n space. So it's certainly going to have a kernel. So, but if I want to talk about how the implicit function theorem is working, I have to invert the derivative. But I should invert the derivative not in the direction of the kernel, but in the direction of the orthogonal complement of the kernel. So I take f times bf of z, restricted to the orthogonal complement of z. I invert that, and I compose it with a diagonal matrix just for, which is the square root of the degrees. Let's forget it. So this is like the condition number linear algebra. This one scales appropriately. 1 by f by lambda, this goes by 1 over lambda. So this is the function that makes sense for f's. Oh, and here I want to take norm of z equal 1. So there's a whole line of zeros. I'm going to define this condition number by taking the norm of z equals 1. So that's this. It's more or less the norm of the inverse of the derivative made into a function of homogeneous of degree z on 0 on projector space, so it makes sense. Okay, so that's this condition number here. And in the linear algebra case, looking for eigenvalues, the condition number mu of a lambda v, where a of v equals lambda v, and v is not 0. This condition number is more or less the same. The norm of a times the norm of a inverse, but now you subtract lambda times the identity, and you restrict to b perp, and you invert this, and you project on b perp. So this is the condition number of the eigenvalue. Note, this condition number, this derivative, is large, means that the root is almost a double root. So somehow this condition number for systems is related to the distance to the discriminant variety. If you have a large, if you have a root with a very, almost an element in the kernel of the derivative, you can make it 0. So it means you can change the system a little bit and make the root into a double root. So this condition number is related to the distance to the discriminant variety in the space of systems. And roots. This one is related to the distance to multiple eigenvalues. Because if there's another vector with the same eigenvalue, then this operator won't be invertible. So this is like somehow close to double eigenvalues, and this one's close to double roots. So these condition numbers are reflecting that geometry. Now I can tell you a little story. So in 1997, we had our first FOCM meeting, and I was chair of the organization at the time. And we had to get plenary speakers. So we had a list of desired plenary speakers, and it was my job to contact them. And on our list of desired speakers was Peter Lax. He was in New York and I was in New York, so I called up Peter. So, hi Peter, you want to come to our meeting in Rio? He said, let me think about it. Then ultimately he said, no, I don't come. And he said, oh, what are you working on these days, Mike? And I said, well, with Steve Snail, there were several things. One of them was with Steve Snail, we were trying to develop algorithms to find zeros with these homogeneous systems. And he said to me, well, that's all right, but it doesn't interest me that much. If it was eigenvalues and matrices, that would interest me. So that was around 1996. Already this job of studying how to find zeros of systems of homogeneous equations, it's taking all my time and effort. It's not an easy thing. But I was working at IBM at the time. I thought, there were lots of practical problems they could give me. And I had the impression that I could have something to say about all of those problems if I just had enough time. It might take me 20 years, but I could say something about the problem for IBM. Once or twice I said something in less than 20 years that might have been useful to them. But it wasn't exactly their business model. So, but here it was kind of similar, working on this question with Steve and other people for all those years. Finally, sometime, I got a graduate student from Uruguay, by the name of Diego Montano. And almost 20 years later, I gave him the problem. So now he did a lot of work, and he's the one who isolated this condition number as being the right one, and studied the condition number from the point of view of probability theory. So in these contexts, now what should we do? What does it mean to solve the problem, to find the answer, when we have a problem that can't be solved exactly? And how do we measure the complexity? Well, Steve and I worked on that a lot in the 1990s. Well, actually, the 80s, starting in the 1980s. And even in 1980, let me also tell you this piece of mathematical law. So Steve was a topologist, first of all, in his life. Then he was a dynamical systems person, extremely important, both of the subjects. And then he somehow, he did a few other things, but then his next occupation was economic equilibrium theory. And then he found a method of finding these equilibria, and there was some kind of global meeting that he and Mo Hirsch defined together. And then they went to conferences, and there were other people. There were guys from Princeton that maybe were even almost in your generation, Howard Kuhn, and what was his name? it'll account to me after a while. So they all had methods. Some of them were using more or less the triangulation methods and degree theory, and Steve was using differential, like Newton-type methods with differential equations. How do you compare them? So Steve's a competitive guy, but he starts thinking, so now there are these methods, how do you really compare them? So that's what got him started in this whole business. How to compare methods, and he started out with the problem of finding zeros of invariant column. That was 1980. This problem here, find the zeros of the system. And his conviction at the time, which I guess he wrote, was fast methods don't always work. You have to choose between speed and surety. And then he did an analysis of Newton's method. Newton's method where there are step sizes. You choose the step size according to some criteria, which you could prove almost always found, prove the fundamental theorem of algebra that way. There was always a root, gave a complexity estimate, gave an estimate of probability of failure, and he got this thing, so okay, with 95% surety, you can solve polynomial systems, but how many steps? Well, the probability of failure was sigma. He gave something like the degree over sigma to the 7 steps. I guess I was visiting in Berkeley. I was still very much involved in analytical systems myself. I was visiting in Berkeley, and Steve had asked me some questions, and I could help him with his thing, which I wasn't getting involved in. But then I saw him give this talk, and I said, well, Steve, this function is not integrable. Your method is infinite average cost. And so then we began a bunch of studies on methods that would be finite, polynomial average cost. And we could do that with one variable, but we couldn't do it entirely for this problem, find a zero homogeneous system. We came close. So here, he is a way of encapsulating a lot of things that we did there. Oops, let me not erase that. And it's his 17th problem. So this is at least one method. This is at least one method is there an algorithm to find an approximate zero of a situation which was C, what was the D, find a zero. The homogeneous system, D. And now it says average polynomial. So I have to tell you what both of these mean. This took us some time to come to this, but for this, he wants to find a point where Newton's method is convergent quadratic. That's what he means by an approximate. So you have to have a simple zero. We're looking for a simple zero. Not every system has a simple zero. Looking for a simple zero, and you want to give it a certificate. The certificate is a point where Newton's method is converging quadratically to that zero, and even with a certificate that says, yes, that's the case. And then you want to consider input systems and average over the whole space of input systems and see that the cost is polynomial, well, let me say cost here. The cost is polynomial in the input size. So now what this is going to be is it can't work. It can't work if there's no simple zero. So it's certainly not going to be an algorithm that works everywhere. And in fact, the algorithm cost may have a pole. So in fact, the algorithm is tending to infinity on some bad, the cost is tending to infinity on some bad subvariety, a divisor or discriminant variety. But yet, on the average, it's performing well. Okay, that's the 17th problem. And then you can say the same for eigenvalue, eigenvector. Is there an algorithm that will find the eigenvalues and eigenvectors approximately same for, so I'll add this same for and the theorem is yes. Yes to both. Let me point out the eigenvalue problem appears to be a quadratic problem. It's quadratic in lambda and v. These are two variables. But actually it's not quadratic, it's really bilinear. If you change a and lambda, v is still a solution. So this problem is actually bilinear in a lambda and v. So it's not really a quadratic problem, it's more like a bilinear problem. That means it doesn't have 2 to the n roots, it only has n roots, and if you treat it as a quadratic, it would have roots at infinity, a lot of roots at infinity. So the problems are a little bit different. Yes, and yes to both. And one of the 17th is due now to Pierre Larez. And the other one, the linear algebra by Armentano, who was the student who started out the problem, Borgheser, Beltran, not in that order, it should be like that. The alphabet, Cooper, and me. So the two papers, you probably find them in archive that answer this question in the positive, with algorithms that do have poles. And how are they done? Well, I only have 3 minutes. Should I stop in 3 minutes? How are they done? The algorithms work by homotopy methods. Let me just draw a picture of what a homotopy method is. Here you have a space of problems, and here you have, lying above it, space of problems, and solutions. So here's the product space, problems. And for the problems, you have the solutions lying above it. In both of these cases, if you throw away the discriminant variety and you throw away the double eigenvalue variety, then this is a covering space. So you have this covering space, and now you pick a path. You have a function you want to solve f1. You take some f0 where you know the solution. This could be either the polynomial situation or the eigenvalue situation. You connect F0 to F1, and then you lift this path. So you lift the path as long as you can by, say, analytic continuation. All these functions are analytic. So you analytically continue this route until you find this route. Of course, that's a very abstract thing. How do you implement this? Well, you can use Newton's method. So you start with an approximation of this route, and now you use Newton's method for a little bit F1. That gives you, so you take Newton's method of F1 with respect to x0, and now the x1, etc. You continue on in this way, and you produce a sort of polygonal path of computed points that are very easily computed, and you come to the end. The question is, how big a step can you take here? How many steps will it take? And there's an upper bound estimate, so the number of Newton steps in both cases is less than or equal, or let's say in the case of homogeneous systems, some constant times the degree, I don't know if there were 3 halves or something like that, times the integral of the condition number of the system and root times the tangent vector f dot j dot dt. So the condition number of this route as you're coming along the path determines how many steps you have to take. He says an upper bound estimate. The same for the eigenvalue problem. You don't need a d here. This is the maximum of the degrees. It's less than or equal to some constant times equal to 0 to 1. Mu of a lambda d times the norm of a dot lambda dot d dot dt. So the problem becomes find a good starting point for these paths. Or maybe use a random starting point. If you could use a random starting point for the random problem, Beltran and Pardo already solved this problem here with a random input. And then they show if you take a random input as your starting point, this estimate gives you a polynomial average over the space of systems where the path you choose is just a straight line. So now the algorithm is just take a straight line from your starting point. So when you want to solve, use this Newton's method along it, use this upper bound estimate, prove that that's a polynomial estimate in the input size of the system. And so that is what the array did. This is a wonderful piece of work. He says his problem is how to get a random starting point. And what he does is he says, look at round off. So if I take the system and round it off to some finite precision, and then I look at all systems that have that round off, well, the difference between that rounded off number and the actual number is a random number. So he uses the input itself in order and truncates to a finite precision in order to produce the random perturbation of the rounded off object. It's a wonderful thing. I very much recommend looking at this paper. It's surely a technique that has meaning in numerical analysis. We already have the rounded off input known. Okay, so that's the method. I wanted to say a bunch more things about this. Let me just read you a quote. quote is from Louis Nierenberg. Louis, one of the prime movers in geometry and PDEs, and he just recently was awarded the Abel Prize for his work. He's not 90 years old. As he was interviewed by the Notices of the American Math Society. And he says, but it is really fun to do mathematics. It is an enormous pleasure to think about mathematics, even though you are stuck 90% of the time, perhaps even more. And then he goes on to say, yes, it is hard to comprehend. He's saying, he's asked, how do people outside mathematics, how can they comprehend it? He says, yes, it is hard to comprehend. You have to be in it, and I think it does take some talent to be able to do mathematics. But it also takes, as I said, Sitzfleisch. You need to be stubborn and have perseverance, and you can't give up. I've been stuck on some problems for years, he says. Well, this algorithm that I just gave to you is a stubborn algorithm. It insists on following this path, even though you may come close to the discriminant variety. So, what I'd be suggesting is, where is the estimate? Did I erase the estimate of the number of steps? Oh no, here it is. In this number of steps, this number of steps involves the condition number along the path. So, several things. One is, this condition number defines a new geometry on the space of systems. Obviously, you want to take geodesics in this new geometry. So you'd like to approximate the paths, approximate the geodesics by some path you can describe in this new geometry. And if you could, you would reduce the problem from the complexity involving with mu to the log of the complexity. So the log of the complexity is the condition you need in order to even to evaluate the polynomial. So you'll be reducing the cost essentially to the same cost as it costs to evaluate the polynomial number of steps. So that would be great to do, and what it suggests is actually what humans, I think, actually do with our own intelligence. When we come up to a problem that we have to solve, or a judgment we have to make, if we make a judgment like that. But it may be wrong. So then there's another part of the brain that doesn't make quick judgments, but then evaluates if your judgment was correct or not. So I would say it's the same here. When you're getting into trouble, if you see that you're progressing, that this number is getting large, do something else. And the something else ought to be that you realize that this problem is coming close, or this path is coming close to a degenerate problem. And so that degenerate problem should have some structure. And then you should write down what the structure of that degenerate problem should be, find one with that structure, and use it to avoid that subvariety. Go around the bad subvariety by knowing a point on it, so you can do something in the normal one. So this should be, numerical analysis may have another aspect to it, and I think it really should be. This estimate is no good. You shouldn't stick to it. You shouldn't be stubborn. If it's getting bad, do something else. And the something else should involve degeneracy. And I would suggest that, there used to be, when I was beginning in graduate school, it was like differential topology Well, we were going to find a countable collection of invariants that would tell you the diffeomorphism type of that. Then we were going to find structurally stable dynamical systems, so that again would be a countable family of dynamical systems that would be almost all of them, and we'd be able to describe them by maybe a countable collection of invariants. So here I'm going to suggest, at least for the you might be able to do that in complexity theory. That you can somehow give a countable tree. Say, okay, if you come to this problem, do this instead. If you're getting into trouble here, do this, do that. And what might the degeneracies be? Well, I would suggest for the homogeneous root problem, it's Tom Boardman theory. So you would say, if I'm getting into trouble here, that means the derivative is getting big. That means I'm close to a system with a double root. That means I'm close to a point on the discriminant variety to an S1 singularity for the projection. So you have S1, and then you have S11, and you have S2, and you have the whole collection, and each one you should be able to tell as you're doing the numerical computation which type of singularity you're coming close to, then adapt to it and use it to help you find the solution. So that's really one great possibility, and even to just take S1 to improve this estimate. That would be already a great start. And in the case of the eigenvalues, it should be the double eigenvalue varieties. So when the numerical system gets in trouble, it should tell you what to do next, and conceivably you could make a decision tree that would improve matters tremendously and even solve all systems. I'm sorry I ran over, thank you. I was just too enthusiastic. And maybe I was too sketchy here. Thank you.
¿Preguntas? ¿Preguntas? ¿Preguntas?
We're here. There's one here.
How would an undecidable problem would look like in your space of problems?
No, that's a great thing, in fact. So I think for this question, I mean, undecidable problems are in P or NP with exact arithmetic. But there are undecidable problems that are not really problems in the approximate world. So for example, it is a problem, does x equal e to the y? Well, this you can't compute. It's not decidable. It's not an algebraic curve. It's an analytic curve. So you can't decide does x equal e to the y. But of course you can approximately. So now you have to really start building a theory where you want to talk about what you can approximate. And it's a question of what is a decision problem, what's the good approximation, what do you want to start building to put into your theory. So for example, in the case of Julius sets of rational iteration, they're normally undecidable in exact arithmetic. You can't decide if it points in the Julius set of even a quadratic iteration. So, but you see all these computer pictures. So what are the computer pictures? They're sort of color-coded. They're color-coded by distance to the Julius set. So you can sort of say, okay, can I decide if you're pretty close to the Julius set? And that maybe you can do, and you can do in polynomial time. And then there was a theory due to Braverman, proving that, I think in most cases, with respect to approximations, you can decide if a point is close to the Julius set or not in polynomial time in terms of the distance it is from the Julius. So the question with decidability depends what is the universe and where you're working. And it changes very, very radically. But I think Felipe Cooker tried to do a theory like that. He wrote a paper. I think it only went so far as more or less the same functions you compute these that are polynomial time computable with these BSS machines that do real Turing machines. But it didn't yet extend into places like either the X or Julius X, and so I think there's still a vast amount to be done there to understand the complexity theory of approximate computation and approximations.
Otra pregunta. You sort of sketched a future for singularity theory inside this, but maybe you can say something about the role of dynamical systems in the whole.
Dynamical systems, yes. Actually, it's already a great problem. So in dynamical systems theory, we know that when you do a computation, it's only approximate. So you're trying to compute an orbit of a dynamical system, you give it to computers, compute the next one, compute the next one, give it the value at this point. But the value at this point is not exactly the value of the function because you had some rounding. So you have a notion in dynamical systems of a pseudo-orbit. So you specify an epsilon, and you say, okay, this is this epsilon pseudo-orbit if f of x is within epsilon of y, then y is there. Then I take f of y and I get z within epsilon of f of y. That's a pseudo-orbit, which I make an epsilon error at every point. And then for certain systems, we can prove that pseudo-orbits we call shadowed by real orbits. So if you have a pseudo-orbit where there's an epsilon error at every point, there's actually a real orbit that stays quite close. So this gives a very good foundation to say that these pictures mean something. In the case that you have hyperbolic systems where you can prove that the pseudo-orbits are really close to real orbits. But now, suppose you're just in the world of pseudo-orbits, and I ask you the question, is that a pseudo-orbit? Can you answer that? Can you make the decision if a definite system of, in the presence of computational error, this may sound really crazy, but in the presence of computational error, if I want to take the decision problem, is a sequence of points that I give you for some given dynamical system, a pseudo-orbit for that system. That is a difficult computational problem. It may be at the heart of the P versus NP question in general for approximate computation. So I think the question of dynamics and pseudo-orbits is a very deep one, and especially from a computational point of view. Sometimes you can say, yes, if the system has certain robustness, you can say, okay, a pseudo-orbit is like an orbit. But then just to check, actually to check with a finite precision machine that a sequence of points is a pseudo-orbit itself becomes a difficult problem.
Thank you. ¿Alguna otra pregunta? Pues agradecemos nuevamente a Mike por su conferencia.